This is Bob Capetta, and this lesson is on expected value. A six-sided die is rolled once, find the expected value. So what do we have to do? We've got to list all of the possible outcomes, and we have six of them. 1, 2, 3, 4, 5, and 6. And with each of those numerical outcomes, we have an associated probability. What is your probability of rolling a 1? 1/6. What is your probability of rolling a 2? 1/6. Probability of rolling a 3, 1/6. All of those are 1/6. So we have numerical outcomes, each with an associated probability. So I make two columns, the x column and the probability column, the p of x column. To find the expected value, you've got to multiply these. So my next column is the x times p of x column. So 1 times 1/6 is 1/6. 2 times 1/6 is 2/6. 3 times 1/6 is 3/6. 4 times a 6 is 4/6. 5 times a 6 is 5/6. 6 times a 6 is 6/6. So we need the x column, the p column, and the x times p column. Now what is the expected value? To find that expected value, we add up all of the elements in the x times p of x column. So these numbers all added up: 1/6 plus 2/6 plus 3/6, 4 plus 4/6 plus 5/6 plus 6/6. All sixth, 3, 6, 10, 15, 21/6 is what it looks like. So my expected value is 21/6. So if I divide top and bottom by 3, I get 7/2 or 3.5. Now what exactly does this mean? What exactly does expected value represent? On average, if you roll a die, you can expect to get 3.5. Now you'll never get actually 3.5, but if you rolled that die hundreds of millions of times, on average, the total would be 3.5. So the expected value is the average behavior, the long-term behavior, what you would expect to get. And that's our idea. Okay, so next concept. 3 coins are tossed. We want to find the number of heads. Describe the number of heads, and we want to find the expected value. So again, 3 coins are tossed. So if it's tossed once, it's either heads or tails. Tossed a second time, either heads or tails. So if we're going to list 2 tosses, it'll be heads, 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 tails, tails, heads, tails, tails. Those are all the possibilities. Now for 3 coins, it's a little harder. We're going to construct our sample space. So we could have all heads, 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 heads. We can go heads, heads, tails, heads, tails, heads, etc. So there we go. There's all 8 possibilities. Written in, I believe, alphabetical order that'll help you keep those straight. So we have 1, 2, 3, 4, 5, 6, 7, 8 elements in our sample space. Now we want to look at the number of heads and find the expected value. So how many heads could we have? We could have 0 heads. Tails, tails, tails has 0 heads. So 0 heads is a possibility. We could have 1 heads. Tails, tails, heads has 1 heads. Tails, heads, tails has 1 heads. Heads, tails, tails has 1 heads. So our possibilities are 0 heads, 1 heads, 2 heads, and 3 heads. And each one of them has an associated probability. Again, 0 heads shows up at tails, tails, tails. That just shows up 1 time out of 8. 1 heads, tails, tails, heads, tails, heads, tails, and heads, tails, tails. That's 3 times out of 8. Exactly 2 heads. Where do we have exactly 2 heads? Heads, heads, tails, heads, tails, heads, and tails, heads, heads, also 3 out of 8. And how many have exactly 3 heads? Just the first one, just 1 out of 8. So what have I done? I've expressed the x column, the numerical outcomes corresponding to the number of heads. I've constructed the p of x column, the probability of each. And my third column is going to be to multiply the x column times the p of x column. So 0 times 1/8 is 0. 1 times 3/8 is 3/8. 2 times 3/8 is 6/8. 3 times 1/8 is 3/8. And if I add all those together, 3 plus 6 plus 3, 9, 12/8. Yes. Expected value, add up those 4, and we get 12/8. Divide top and bottom by 2, what do we get? 3/2 or 1.5. Let's think about what this means. If you flip a coin 3 times, how many heads do you expect to get? on average, you would expect to get about 1.5 heads. About half the time you would expect to get heads. So if you flip the coin 3 times, you would expect on average to get 1.5 heads. Here's our next example. A child has 2 spinners. One has 4 equally sized regions labeled 1, 2, 3, and 4. The other has 3 equally sized regions labeled 1, 2, 3. The child spins both and then determines the total. So find the expected value. So the lowest number I can get on this spinner is 1. The lowest number I can get on this spinner is 1. So the lowest possible sum I can get is 1 plus 1 is 2. What's the highest possible sum I can get? Highest possible sum on this spinner is 4. Highest possible on this spinner is 3. Highest possible I could get is 7. So I guess my possibilities are 2, 3, 4, 5, 6, and 7. But that is not the sample space. Remember, the sample space has to be all equally likely outcomes. What I need to do instead is I need to think 1 with 1, 1 with 2, 1 with 3. 2 with 1, 2 with 2, 2 with 3. 3 with 1, 3 with 2, 3 with 3. 4 with 1, 4 with 2, 4 with 3. That would be my sample space. So my sample space consists of those 12 outcomes. Now, the child is adding these together. So 1 plus 1 is 2 shows up how often? 2 only comes in one time. This is the only time that we get a sum of 2. So 2 has a probability only of 1 out of 12, whereas the other numbers have different probabilities. So we're going to make our chart, our x chart with our numbers, our p chart with our probabilities, and then eventually multiplying the x times p to get the expected value. So again, we started with 2. 1, 1 is the only case. 1 plus 1 is 2. That shows up one time in 12. How about 3? How often do we see 3? Here's 1 plus 2. Here's 2 plus 1. Any other 3s? I don't think so. So 3 shows up 2 times in 12. How about 4? Where are our 4s? 1 plus 3 is 4. 2 plus 2 is 4. 3 plus 1 is 4. So we have 3 of them that gave us 4, so that's 3 out of 12. 5, where are our 5s? 2 plus 3 is 5. 3 plus 2 is 5. 4 plus 1 is 5. So again, I get 3 out of 12 for my total of 5. How about 6? Well, I believe I have 2 possibilities for 6. 3, 3, and 4, 2. 3 plus 3 is 6. 4 plus 2 is 6. So that's 2 possibilities in 12. And then 7, the only case of 7 is 4 plus 3. Now let's make sure that all the numbers in the p column add up to 1. 1, 3, 6, 9, 10, 11, 12. 12 twelfths indeed. So this can make sense as long as all of those numbers in the p column add up to 1. If they don't, then you must have made an error. Now to find the expected value, I've got to multiply the x column times the p column. 2 times 1 twelfth is 2 twelfths. 3 times 2 twelfths is 6 twelfths. 4 times 3 twelfths is 12 twelfths. 5 times 3 twelfths is 15 twelfths. 6 times 2 twelfths, 12 twelfths. 7 times 1 twelfth, 7 twelfths. What is our expected value? We're going to add all of these together. Add the numbers in the x times p column. So 2 twelfths plus 6 twelfths plus 12 twelfths plus 15 twelfths plus 12 twelfths plus 7 twelfths. And what do we get? We get 54 twelfths, which I could divide top and bottom by 6 to reduce that fraction. And what do I get? I get 9 halves, or 4 1/2. So if we do this experiment many, many times, do the first spinner and then do the second spinner, our total on average will be 4 1/2. If we do it millions and millions of times and look at the overall average, we would expect it to be about 4 1/2. And that's what expected value represents, long-term behavior. We're going to take a look at expected values for games of chance. And friends, the reality is that any kind of legal gambling makes no sense from a mathematical perspective because the house always keeps the money. And this is a nice example. So the Pick 5 game from the Florida Lottery requires a player to pay $1. And if the player correctly picks a 5-digit number, the player can earn a maximum prize of $50,000. And here is a site you're going to take a look at the rules of the game. So there's two possible outcomes. You're going to pay $1 to play, so the ticket costs you $1. So if you do not get the correct number, you lose $1. If you get the correct number, you win $50,000, but you already paid the $1 to play. So in essence, you win $49,999. Except this game is even worse. In most states, you pay state income tax on your winnings. That is not the case in Florida, but in most states, they get extra money that way. And also, this is the maximum prize. Looking at recent payouts on the web page, on the Florida Lottery web page, it's been more in the neighborhood of $23,000 to $25,000. So they're not even paying this. So this is the best case scenario. So we need to determine what's our probability of winning. Well, we've got to correctly choose a 5-digit number. So we want to use the fundamental counting principle to do the analysis there. How are we going to do the fundamental counting principle? We have a 5-digit number. So let's assume for a given day that the correct answer is 63709. How many 5-digit numbers are there? How many choices did you have? Well, for the first digit, it could have been a 1, a 2, a 3, a 4, a 5, a 6, which you're saying is correct, a 7, an 8, a 9, or a 0. So you had 10 choices for the first digit, 10 choices for the second, 10 for the third, 10 for the fourth, and 10 for the fifth. So each one of those digits had 10 possible choices. So how many total choices did you have? Right? 10 times 10 times 10 times 10 times 10. Which is 100,000. And, no surprise, your largest 5-digit number, 99,999, and then also includes 00000, that gives you 100,000 possible 5-digit numbers. Only one of them is the correct 5-digit answer. So your probability of winning is 1 out of 100,000. So, if we are interested in this, what are we going to do? We're going to make a table. Two possible outcomes, either winning or losing. Either winning $49,999 or losing 1, together with their expected probabilities. So I have an X column and a P of X column. The winning, the $50,000 prize minus the $1 ticket, is only 1 in 100,000. Whereas losing $1, 99,999 times out of 100,000 you're going to lose. So X times P gets me here. So 49,999 out of 100,000 plus negative 99,999 over 100,000. What is our expected value going to be? Adding those two numbers up, remember the expected value requires us to add the two numbers in the X times P column. Negative 50,000 out of 100,000, which means negative 50 cents. Now what does this mean? It means if you play this game, it costs you $1, you can expect to lose 50 cents. What it means is that the state of Florida, in essence, keeps half of the money and pays the winners the other half of the money. So you can see the real winner of this game is the Florida Lottery. And the same thing holds true for casino gambling. If you play roulette, there's about a 5% house take. So every time you play roulette, the house keeps about 5 cents on the dollar. Sports wagering, if you do that with a legal sports book, it's the same thing, that the expected value is losing about 5%. If you bet $1, you can expect to lose 5 cents. So you can see this lottery is even worse than casino gambling. Slot machines, you lose money very quickly. You play lots and lots and lots of times and lose a small amount every time, which is why the casinos make a fortune. So from the perspective of expected value, gambling is not very smart. But back to our basic concept, you list all the possible outcomes, all the probabilities, multiply the X times P, add them together to get your expected value. And that will conclude this lesson.